Hello everyone, thank you for being here early. We're going to get started in just a couple minutes. I'll give everyone a little time to arrive. Make yourselves comfortable, get your speakers turned up. Be with you in a moment. And I think we are live. Hello from the nicest studio I've ever been in, and welcome to Data Acquisition 101. Thank you all so much for being here. My name is Derek Burrows. I'm the Product Marketing Manager for Data Acquisition here at NI. I'm a certified LabVIEW architect. I've been working with data acquisition and test and measurement customers for about 5 years now. And I've seen a lot of the different applications that they work on and a lot of the different challenges that they run into when they're trying to build a DAQ system. One of the things that I hear a lot from our customers is that it can be difficult to understand what the best choice is or even where to start when they're presented with hundreds of different data acquisition devices, hundreds of different providers for those devices. It's hard to know what specs matter. It's hard to know what is, jargon and fluff versus what is really important for your system. And so we made this webinar in order to help demystify DAQ. We're going to be talking very clearly about how to build your next DAQ system and everything that matters going into that. The webinar portion is going to be about 45 minutes of this hour, and then we're going to have a live Q&A for the remaining 15 minutes. So we're going to talk through the basics, really understanding how to read a spec sheet, those things that really need to be there for you to take a quality measurement. We're going to move beyond the basics and ask questions that will help inform what type of system you should be considering for your next DAQ application. We're going to talk through software selection and the types of hard questions you should ask yourself and ask your team before you standardize on a particular piece of software for your system. And then finally, we'll run through a real example of building a sample system and talk through a little bit on how to buy DAQ systems as easily as possible. I also want to make it clear that we have specific goals and specific non-goals. By the end of this webinar, I'm hoping that you'll be able to understand specification tables at a glance. Really get to know the difference between different products on a table full of products without needing too much additional research into the data sheets. You'll be able to ask tough questions that will help you build a better system. And we're going to talk very explicitly about the NI hardware and software choices that are available to you. I've got all my lovely DAQ hardware with me here today, so we can talk this through in a little more detail. The things you will not get from this presentation are, number one, learning how to take a sensor measurement. We have lots of content for this. I've actually included a link in the resources, probably over here, that will link to the Sensor Fundamentals webinar series. It's a great set of content that introduces very basic DAQ concepts, shows you how to take thermocouple measurements, and even shows some demos taking measurements with LabVIEW. That's not what this seminar is about. We are going to be talking more specifically about everything you need to spec and select a system, not how to use that system. You also won't leave this seminar knowing exactly what product you should use. We will help you narrow down the options so you have an idea of what the right type of system is for you. But you're not going to walk out of here saying, the USB 6003, that's my device. This is exactly what I need. We're giving you the tools you need to take your test requirements and translate that into a great starting point for building your next DAC system. With that said, before we jump into the basics of DAC, I also want to introduce NI's data acquisition systems. Now, there's a very good chance you are already familiar with a lot of these different hardware pieces, but I want to introduce a split between these devices. On my right, your left, you'll see these DAQ devices. These are devices that plug into a PC and make it pretty quick and easy to start taking measurements. They often work via plug and play. And on my left, you'll see our data acquisition systems, modular hardware that allows you to customize exactly what you need for a given measurement application. So we'll be talking through devices, these USB PCIe devices, as well as data acquisition systems, and comparing the pros and cons of using each as we talk through these different DAC considerations. So keep these in the back of your mind. I'll be picking them up and playing around with them as we go. The DAC devices are over here. CompactDAQ Systems are over here. And then our big PXI chassis is over here with all of the individual I/O modules that you might use in a given application. One more thing to look out for as we go through these topics are these notable slides. We've listed out some buyer's tips and some inflection points for you as you go through this journey. The buyer's tips are really just things to keep in the back of your mind that will make you a pro at choosing the right DAC system. These are considerations that potentially not everyone is thinking through as they select their next DAC system, and they can save you a lot of headache down the line. The inflection point slides, those are a slightly different kettle of fish. We are talking about the decisions that you make for your DAC system that will narrow down your choices into one of these options, whether a DAC device is right for you, a DAC system like CompactDAQ, or a DAC system like PXI is the right fit. So these green slides will be nice and screenshotable, so if you want to have those to refer back to, I recommend skipping to those as you flip back through these slides. And without further ado, let's start the presentation with the basics of DAC. We're going to talk through understanding your channel counts and how that relates to your DAC systems, as well as how to know the base specifications that matter most for a data acquisition system. And we'll start by redefining what goes into a data acquisition system. This should be familiar to a lot of you, but if not, there are three basic components to any individual DAC system. There are the sensors and the signals that you are trying to measure, the data acquisition device that translates those signals into something your computer can understand, and then you have the computer itself with the driver software and the application software you need to understand that signal. We're going to start by talking a little bit more about the sensors and the signals. Now, signals come in two different forms. There are digital signals, often represented as sort of 0 volts or 5 volts, where your signal is really one of two possible states, and your DAC device only cares to measure one of two possible states. These are useful for a variety of different applications. You may hear terms like pulse waveforms, pulse width modulation. Things like encoders use digital signals to transmit their data. So digital signals are very common and a little bit easier to measure because there's really only two states that matter. Analog signals are more complicated because they can be any value with respect to time. This is a classic, sinusoidal waveform that you might be taking in from a power supply or something like that. And these analog signals are typically read in as voltages. So those are signals. Let's talk a little bit about sensors now. A sensor is a device that translates a physical phenomenon into a measurable signal. So in this example, we have a photovoltaic sensor. As light shines down onto that sensor, the voltage that is output from that sensor increases. And so that is a pretty simple way to transform a real-world phenomenon into an analog signal that you can then read in with a data acquisition device. There are a lot of different sensors out there that you may find useful in your data acquisition applications. And for those of you who are working on a data acquisition application right now, I'm sure you're seeing familiar names: thermocouples, microphones, strain gauges. These are some of the most common sensors that engineers and scientists use every day. So with those definitions in mind, we can jump into step one of building your next data acquisition system, which is understanding your channel counts. Your test requirements, or your measurement needs, will probably include a mix of signals, like voltages, currents, and on-off digital signals, sensors like thermocouples, accelerometers, strain gauges, and more, actuators, things like LEDs and motors and speakers that you want to control from your device, and specialty I/O. This is a grab bag for anything that doesn't fall into the categories above. Communication protocols are a great example of these. Your DAC selection process will start by sorting your I/O into these 4 categories. This, coincidentally, is how NI separates a lot of our DAC products on the web. So if you fit them into these buckets, you'll be able to easily understand, okay, there's 8 analog input channels. I have 8 analog input signals that I need to measure from. These 2 correspond quite nicely. Let's make that a little more real with an application like in-vehicle data logging. This is based off of a real customer's application that I've helped through some of these selection challenges. And when it comes to their measurements, they had largely analog inputs that they cared about. They were trying to measure as much as they could about the car as it was driving through a racetrack. And they had some voltage signals they needed to measure, as well as a few different sensors that they wanted to measure from. When I'm building out my test requirements, I like to separate my signals, which are just my voltages, from my analog sensors for reasons that will become very clear in just a little bit. Pro tip, it's because we have modules that are designed specifically for the sensors that will make your life a lot easier. There's also some things like digital I/O. We have encoders which will be capturing the speed, the velocity of the tires as they turn. That is a digital pulse train signal, and so we need to measure that in as well. And then we have some specialty I/O, which includes things like CAN. CAN communication is an automotive network that lets me understand the rest of the health of the vehicle. So it's nice for my data acquisition system to be able to understand all of that as well. So this is a really easy framework for breaking out your different channel needs. This can be applied to a whole bunch of different tests. And I'd encourage you to think about your I/O in this sort of separated bucket style as you're building out your DAC system. Once we understand our channel counts, we can move into our data acquisition devices. And let's start by talking about the first big part of a data acquisition system, which is the signal conditioning. Analog signals can be very, very messy. On the left side of this slide, you will see a noisy, unfiltered, low-level signal, picking up a whole lot of different EMF noise from the atmosphere, from the room around it, from power supplies that are just in the space you're in. And on the right, we have a nicely conditioned signal. It's the same data, just we've removed all the fluff that we don't care about, because what we really want is that main waveform. There are a lot of different ways that you will need to condition voltage measurements. And you will see DAC devices that offer a mix of all of these different sensor signal conditioning types. Amplification beefs up a signal so it better fits into your device's range. Attenuation is great for high voltage signals that would fry your device if they went in just like that. So the attenuation circuitry will make it into a more sensible level of voltage that your analog to digital converter can understand. Filtering will remove noise from your system, and isolation helps remove noise as well as protect your channels. I went fast through those because there's a whole series of webinars we could do on signal conditioning for voltage measurements alone. But I want you to just remember that these are the types of signal conditioning you should look for whenever you purchase a DAC device. If they don't have some amount of filtering, some amount of isolation, chances are you're going to end up with worse data as a result. Next, we can talk about signal conditioning for sensors. A lot of the common sensors that you use will output a voltage signal, but they tend to be aided by having some additional signal conditioning built in. A thermocouple is a great example of this. A thermocouple you can read in as just a pure voltage, but it's much more useful and it's a much better measurement if you include a component of signal conditioning called cold junction compensation, which really allows you to capture what the temperature actually is, as opposed to having relative references to each other. There are a lot of signal conditioning types that apply to different sensors. We've listed a few of them here. But one of the things that I'd really encourage you to do as you build your DAC system is to look for preconditioned I/O. This is our first buyer's tip. When you are buying a new DAC device, chances are you'll be able to get by reading in just a voltage. But there's also another chance you're going to be sitting there fiddling with breadboards and wires trying to build in the signal conditioning that you need to take a good measurement. You can save yourself that hassle by, instead of using just a regular voltage input device, using a thermocouple input device instead. These devices will have cold junction compensation and similar circuitry built into them, so you don't need to do any of that external wiring. The 9210 we have shown here actually also has connective ports for mini TC thermocouples. They're designed to make it as easy as possible to acquire data from these specific types of sensors. So this will save you a lot of time and a lot of pain as you build your next data acquisition system. And this buyer's tip actually brings us to our first inflection point as well. When it comes to, have I gone too far? Okay, we're there. When it comes to conditioned I/O, there are limitations on devices like these multifunction I/O devices. NI's DAC devices tend to be more single purpose. They're really good at reading in analog signals like voltages, but they don't come with signal conditioning for sensors specifically. Oftentimes, you would need to do some software processing or build out some external circuitry in order to take a quality measurement from a variety of different sensors that are a little needier. If you want a system that makes use of preconditioned I/O, you are probably locking yourself out of the data acquisition devices space and bringing yourself into the CompactDAQ PXI DAQ Systems space. Now, I'm going to mug to this camera. A CompactDAQ device actually has a lot of different modules to it. There are over 70 different modules that are available for a CompactDAQ system, and most of them are sensor-specific I/O. I have here the 9234. It's a best-selling sound and vibration module. It comes with Bnc Connectivity. I'll bring in an accelerometer here, and you can see that it directly connects to my sensor because this was designed with this particular application in mind. This device knows how to filter out the data that isn't as important for an accelerometer or a microphone measurements, and it knows how to build up the right signals for that dynamic signal acquisition type of measurements. So devices like these are incredibly popular for a reason. They save you a lot of the headache and a lot of the custom wiring you need to do in order to take a quality measurement. So definitely consider using preconditioned I/O devices. And if you're using preconditioned I/O devices, definitely consider building a DAC system as opposed to using a more single-function DAC device. Another key inflection point on a very similar note is specialty I/O. Now, when we talk about specialty I/O, we're talking about things that we don't typically consider as data acquisition, measuring things beyond just a voltage or sensor measurements. These can be things like communication protocols, or they can be very unique types of measurements, including things like RF signals for testing 5G networks, for testing radar systems, anything else that you might need. For those applications, it can be really helpful to have systems that can extend beyond the world of DAC. So once again, our DAC devices are pretty much invalidated right off the start. These guys are made for DAC. They are single-function DAC. They do not have the modularity required to bring in little bits and pieces from other types of test. CompactDAQ is mostly designed for data acquisition and for sensor measurements. There are a few modules that will give you access to things like automotive networks, because we found there's a lot of cross-pollination between the different DAC types of tests that are sensor heavy and the types of communications that you might need for those. So CompactDAQ has access to some of this specialty I/O, but when you're talking about the widest variety of other types of measurements in a data acquisition system, PXI is your best choice. PXI has access to a pretty staggering amount of different types of I/O, and I'll leave it at that because there's a lot more I could say. But if you have a desire to bring in other types of I/O into your data acquisition system, consider using these system-level things. Consider investing in the beefier PXI systems for access to more of that I/O. So that brings us to step 2, understanding data acquisition specifications. We've tabulated out our different channels. Now we need to understand, now we need to understand more about each of those different channels. Any individual signal that you're reading, you will probably have to know what the precision of that measurement you need to read from is. If you are measuring, for example, that photovoltaic sensor, chances are you want to be within 0.1 volt precision of the actual real-world result. Precision is translated to DAC as resolution. The amplitude of the signal that you're trying to measure is translated into range, and the signal frequency is translated into rate. These DAC specifications are known as the 3 R's of DAC, and they are going to be the most important specs for you to understand for you to tackle your next measurement application. So before you start choosing your DAC devices, know the precision, the amplitude, and the frequency of the signals that you're trying to measure from your channel count list, and then you'll be able to make the right choices for your DAC device. Let's talk about these in more depth. Resolution is a really important concept, possibly the most important concept when it comes to building your data acquisition system. The resolution of your analog to digital converter defines how many total values that signal can be. 3-bit resolution means you have 2 to the power 3 total options across your entire range. So you can see here, we are following the shape of this sinusoidal curve, but it's not great. For the whole little top parts of that curve, we are missing out on a lot of that individual detail that we might want. To get a better measurements, we need to increase our resolution. The 6-bit resolution is far, far tighter on that curve and far more useful from a measurement standpoint. It's important to remember that resolution scales exponentially because each increase in resolution effectively doubles the amount of points you can have on your given signal. This brings us to another buyer's tip. Resolution scales exponentially, and prices will scale similarly. Not exponentially, but similarly. The USB 6000 is a great example. It is an entry-level DAC device that takes pretty quality measurements for a pretty low price point. It has 12 bits of resolution. The USB 6002, on the other hand, an upgrade of this device, costs over $400. That's more than twice as much for only 4 extra bits of precision. That can feel a little uncomfortable to some customers because it feels like you increase your performance by like 30-ish%, while in reality, you've increased your performance by 16 times. A few extra bits can add a lot of extra precision to your system, but expect the price of those higher resolution cards to scale as a result. And that brings us to input range. Input range is another really important concept when it comes to data acquisition applications, because your ADC, your analog to digital converter, will be set to measure across sometimes let's say a 10 to minus 10 volt range. The resolution applies to that full range. If you're only measuring a subset of that, for example, a 2 volt signal out of that 10 volts, you're getting a fraction of the resolution that you paid for. One of the best ways to address this is to have selectable input ranges. Most NI cards offer a selectable input range, where you've got the maximum minus 10 to 10 volts, but you can also scale that down to plus or minus 5 volts, plus or minus 2 volts, plus or minus 1 volts, what have you. This allows you to take a much higher quality measurement whether you're taking a 10-volt signal or a 2-volt signal, because your device can scale that data to make full use of your resolution at any one of those different ranges. So make sure that when you are looking through your list of channels and looking through the amplitudes of those signals, you've got cards, data acquisition cards, that can adapt to that range of amplitudes. If you try to use your 10-volt cards for your 0.1 volt signals, that might not give you the resolution that you need in order to take a good measurement. Finally, we come to sample rates. This is the speeds and feeds, what everyone asks about first when it comes to taking a quality measurement. And there's a very good reason for this. Sample rate is something that when you get it wrong, it can really change how you understand a given signal. Let's take a look at this waveform. There's obviously infinite points across time that it could be at any given point in time. And if you were sampling it infinitely, you'd get this exact waveform rinsed out. But devices are not perfect, and we need to set a rate at which it takes a sample across this waveform. If we sample too slowly, for example, every 0.1 second or so, we will get a waveform that is vastly different than what is actually trying to be represented. Speed that up a little bit and we can get something even worse. It's a little bit closer to the shape, but it still looks bad and jagged. And that wouldn't make for a great test result. When we get faster, when we get to 10 times the speed of the signal that we're trying to measure, that's when we start getting quality data. That's when we're representing the shape and the frequency well. This can be easily represented by the Nyquist theorem. You may remember this from Electrical Engineering 101 if you were in such classes. To accurately represent the frequency of a signal, you need to have a sample rate that is at least 2 times the minimum frequency component of your signal. In order for you to capture the shape and the frequency of your signal, you need to be sampling at least 10 times faster than the minimum frequency component of your signal. And naturally, NI recommends sampling at the very minimum 10 times the frequency, and really you should be sampling a little bit faster in order to get the nuances of that signal as well, especially when it comes to little peaks and valleys that may happen for less consistent signals. This brings us to another buyer's tip, and one that I think is one of the least well known in the data acquisition space, and that's simultaneous sampling. There are 2 technology types when it comes to building out a sample rate. There's multiplexing and there's simultaneous sampling. Multiplexing happens when you have a lot of different channels in a given DAC card and you are using the same ADC. While your sample rate may be 100 samples per second, that 100 samples per second is shared among those 8 channels. So your first sample will go to channel 0, your second channel will go to channel 1, and suddenly you've divided down your sample rate for each of these channels quite significantly. The solution to this is simultaneous sampling. Every single channel has its own ADC. The cost of simultaneous sampling is higher, but you will know that you will be able to measure at your maximum sample rate no matter what. Always, always, always look for multiplexing versus simultaneous sampling. There's an easy shorthand you can remember. Multiplex devices use samples per second. Simultaneous sampling typically represent their sample rates as samples per second per channel. So keep an eye out for that as you're shopping. It will save you headaches in the future. And now we've covered the basics, those key pieces to buying a DAC system. And we can put it into action right now. So this is a screenshot from the PXI analog input module page. These guys we have right over here on the desk. And what we can see is that we've covered all of the key specs you need to make your measurement. The channel counts are on the left. You need to understand how many channel counts you need for that particular measurement type. You have the sample rates. We can see here in those sample rates that these are listed as kilosamples per second per channel, so we know it's simultaneously sampled. We have the resolution of these devices. These go from 16 bits up to 24 bits, so you've got a lot of resolution. PXI is known for being very powerful and having really high resolution, high speed cards. a lot of selectable input ranges. Once again, this will allow you to make the most of that high resolution ADC. And then finally, we have the signal conditioning options that are available, including filtering, more filtering, and isolation. So with this quick lesson, we've already covered most of the things you will need to make heads or tails of a given specification list as you're comparing products online. To recap, step 1, list out the channels that you need. Sort them into signals and sensors, and then bucket them into analog input, analog output, digital I/O, and specialty I/O. Step 2, for each signal that you need to measure, make sure that you know the precision that you need, the amplitude of the signal, and the frequency of the signal. And then you can find the right DAC device for that system with the right resolution, input range, and sample rate that you need to take a good measurement. So that's the basics of DAC. Let's go into beyond the DAC basics. The unofficial step 3 for this section is understanding the right questions to ask to help you narrow down your choices. We've already talked through some of the considerations that help you choose between a DAC device or a DAC system. Let's bring up a few more considerations. Question 1, what bus is right for my measurement system? There are a lot of different ways that you can communicate with your device on this table. Right over here, and I'll turn to product camera, we have these PCI and PCIe devices. This is a bus technology which allows you to plug in cards into a desktop PC or a tower PC. You typically have to turn off the computer first, plug these guys in, turn it back on, so it's a bit more of a hassle, but they offer pretty fast throughput, and they allow you to transmit a lot of data quite quickly. The older PCI standard has a much longer connection, which is ironic because it's actually quite a bit slower and has lower throughputs than the newer PCIe connection, which is just these two little nubs here that plug into your computer. Technology is getting better and faster every year. A very common type of bus that you've probably interacted with many a time before is USB. So we have a few different USB products online as well. We have USB DAQ devices, like these guys here. And we have USB DAQ systems, like CompactDAQ. We have a number of USB bus CompactDAQ devices as well that transfer the data back over USB. USB has one of the slower streaming capacities, only 60 megabytes per second for USB 2.0. With that said, most measurement applications don't even come close to 60 megabytes a second of streaming data. It will really depend on your specific application needs. But USB is very popular in the industry just because of its portability and its flexibility. Plug and play is really, really easy for customers to get up and running with. Another common bus that you've worked with many a time, I'm sure, is Ethernet. Now, we have Ethernet CompactDAQ systems, and these guys tend to be similar value to the USB in terms of it's easy for you to connect it to a PC, no need to plug into a tower, and these guys are relatively portable. In fact, over Ethernet, you can connect a bus that's much farther away, potentially even hundreds of feet away from your computer. You could snake out your CompactDAQ system, no problem. One of the advantages of using a Ethernet system is that you can do distributed measurements with one. You could take multiple different CompactDAQ systems and daisy chain them together over Ethernet so the data is transferred from one to the next, back to your PC. This is really helpful for what I'm informally calling big stuff DAQ, when you need to measure a system that's very large in space and you'd like to set up individual DAQ nodes across that system. It's also helpful for when you just need more channels in your system than an individual CompactDAQ chassis can provide. And then finally over here we have PXI and PXI Express. This bus technology is very similar to PCI and PCIe. The streaming rates are very similar, but the synchronization capability of these buses is parallel to none. So PXI allows you to consolidate a whole lot of different data very, very accurately compared to each other. And PXI systems tend to be just beefier than most of our other systems. You'll be able to fit a lot more channels into one with this guy. So PXI becomes a great choice in that case. Which one is right for you depends on your application needs. Try to get a sense for how much data you will be transferring back and calculate out how much streaming you will actually need to do. Chances are you're going to make your decision based off of portability and convenience, as well as the other factors we're going to discuss, as opposed to the bus alone. But if you are streaming a lot of data, make sure you think this through. So the next question you should ask yourself is, how will you connect your signals to your DAC device? This one is really a choice of convenience. There's a lot of different ways that customers choose to connect their signals, their wires, to their data acquisition devices, and NI has accommodated a variety of those. Screw terminals are easily understood. Bring it over to this camera here. You have entry holes for your wires along the side. You screw those in, and that forms your connection quite tightly. These are cheap to make. These are relatively accessible, and you'll see them pretty much everywhere. They're kind of the standard. What's nice about screw terminals is that you don't need additional accessories. Everything connects right into your device. Bnc connectivity, on the other hand, it's a little more secure. They have these little locking mechanisms, these locking pins built in. And they're very popular with certain types of applications. Microphones and accelerometers love to use Bnc connectivity because that's how the sensors are outputting their data anyways. Once again, these guys provide direct connectivity, no additional accessories required. There's also a lot of different data acquisition devices that come with these connectors on the front plate. This is a card that could take in 64 different pins. It wouldn't make sense to have 64 different wires coming off of your PCIe card. So instead, you use a connector to transfer that data over a cable to a terminal block, where you could then screw in your different measurements one by one. It's really up to you what makes the most sense for your particular application. So we've covered how do you choose the bus, how do you connect the signals. Now let's get into some things that are a little more abstract. For example, how often do my test needs change? There are a lot of different test roles. There's a lot of different measurements applications where you will be changing the types of measurements you do every day. Sometimes you're being handed 7 different DUTs or devices under test in a single day. And so you need to measure thermocouples for the first 3, and then you need to measure accelerometers for the latter ones. Sometimes you are working in a system that has no changes. You're measuring the same boards day in, day out, just a handful of voltages, a handful of digital I/O, and you're passing that right through. For people where changes are rare, a data acquisition device can be a really cost-effective way for you to create a system that lasts for a long time. You could also use a DAC system if you have I/O needs that require a data acquisition system. But the fact that you don't need to change it very often means that either of these platforms are quite useful. As you get into more frequent changes with big changes in the I/O you're taking, that's where a modular data acquisition device becomes really useful. You could swap out your sound and vibration card for a temperature module as the particular needs came up. So my recommendation is for those of you who are changing up their systems relatively infrequently, but still often enough, you could buy a system that meets your needs today, and then when you need a new card, you could buy something for that particular test and wait the week to get that stuff in. For people who are doing loads of different tests all the time, it can be useful to start building out a hardware cabinet. I've met with a lot of different customers who have a little cabinet full of C-series modules or PXI modules that they'll slot into their system as needed, so they don't have to have any downtime between their tests. And there's a lot of value to that as well. So think through how often your tests needs will change, and that will help inform what system is right for you. Where will I take my measurements? This is one of my favorite questions because I think it's one of the big differentiators between these devices we have on the table today. Data cannot always be taken in the lab, and your DAC device might need some amount of ruggedness. A lab is obviously very safe and clean, but a big hangar might be a little dusty. Field environments will have some dust, and even if it's a sunny day, there's some chance of vibration or dropping the device as you're moving it around, which might require some shock and vibration protection. And then we have the very extreme end of things like test cells and temperature chambers, where you are purposefully putting a device or a system through extreme conditions. To take measurements in those places, it can be useful to have something even more rugged, maybe something that's really resistant to temperatures or even waterproof. This is one of the big inflection points between these devices. We have a pretty far-reaching scale of ruggedness available in the NI product line. These data acquisition devices, especially these PCI and PCIe devices, they are not well suited for any kind of hazardous environments. They're not designed for tests outdoors, and you certainly wouldn't want to lug your tower PC outside anyways. So these should be kept inside the lab. If you're in the lab, you're golden. PXI is a big, beefy system, but number one, it's very heavy. And number two, the cards that you have to slot in are pretty exposed to the air. They look a lot like these PCI cards. So dust getting into the connectors can be a real issue in more dusty environments. So my recommendation would be to keep these largely in the lab as well, but they have a more moisture resistance, a little more shock and vibe resistance that helps them out in more environments. CompactDAQ, compact and durable. These guys can take a bit of a hit. They've got decent shock and vibration ratings. They can last through minus 40 to 70 degrees Celsius for some models. So these can be well suited to outdoor tests. Oftentimes you'll need to keep them in an enclosure though, because they have no IP rating, no water protection. So it'll be a little bit tougher. They can resist dust. They're IP40, I believe, but they wouldn't be able to resist water. I've included a bonus product on this list, and that's FieldDAQ. I didn't want to bring it up because it's a more niche use case than some of these other products, but NI FieldDAQ devices are really designed for that extreme scale of ruggedness. They are IP67, similar to a lot of your cell phones potentially, which means that they are waterproof, they are dustproof. These guys have the highest temperature ratings of any NI device. So if you need really rugged test environments, FieldDAQ might be right for you. It's available for a variety of different sensor I/O, as well as your standard voltages and that sort of thing. And now, one more question in this section. Do I need my DAQ investment to last? And this is a bit of a rhetorical question, but it's one that I don't think enough customers are thinking through. You are making an investment into a DAQ system, and downtime for your tester can really hurt your business. So it's important that you protect your investment with some amount of services, not only in case something breaks and you can send it in repair, but also so that you can get your devices regularly calibrated to make sure that they'll be functional for the long run. There are a couple different service plans offered by NI. There's the standard, which offers you an extended repair coverage, as well as some system assembly type stuff if you want to get a pre-configured PXI and CompactDAQ. And there's the premium offering, which gives you faster turnarounds for new systems and a whole bunch more functionality baked in. And that brings us to the end of the hardware considerations. Let's jump into selecting DAC software. I'm running a little bit behind on time, so I will go ahead and speed through these. But you should be aware that software tends to be the most important part of building your measurement system. The cost of your total measurement application isn't just the hardware and software sticker price. It's the amount of time you and your developers are spending building out your test systems. A survey of data acquisition customers and prospects found that 64% of most data acquisition systems are spent on development, software development. When it comes to building software for your data acquisition system, there are a lot of different options available to you, but NI categorizes them loosely into application software, software where you interact with your I/O through menus and drop-down lists, and programming languages, which give you full control over how you will design your test, but requires some amount of programming knowledge. So on the left, we have FlexLogger and LabVIEW NXG. These are great examples of application software in that you can take good measurements with both of these tools by just clicking through some drop-down menus. FlexLogger is really designed for data logging customers who want to stay in that configuration-based environment for anything they want to tackle. LabVIEW NXG has some of those configuration-based elements, but is designed to ease you into that programming curve. So it's a great fit for people who aren't necessarily super adept in any one particular language, but are looking to program for their next application. The programming languages available to you that NI sells are LabVIEW NXG, Lab Windows CVI, and Measurement Studio. LabVIEW is a name that I'm sure most of you are familiar with. It's a graphical programming language that was designed with test and measurement in mind and makes it really, really simple to communicate with your hardware, bring in third-party I/O, and do a whole lot more. But that's not the only option when it comes to programming. You can program in C, you can program in Python, you can program in C#, any of the .NET framework stuff. And you can program in MATLAB. There's a data acquisition toolkit in MATLAB now that lets you take quality measurements. So NI has invested a lot into our NI DAQMX driver to make it easy for you to communicate with any different software that your team may already be specialized in. And the NI DAQMX driver is the same driver for all of the devices here on the table today. The functions in NI DAQMX when it comes to programming are actually the same whether you're using them in LabVIEW and C. So if you have a customer or you happen to be very familiar with LabVIEW, you can train up your colleagues in the basic syntax of making DAQMX function calls and really help each other learn how to take your data acquisition measurements more easily. Which brings us to this drastically oversimplified flowchart. There's so many different things that go into choosing the right software for you. I recommend that each and every one of you try out some of the free evaluations to get a sense for the software before you jump into programming. But this is the flowchart that I see most of our customers go down as they try to choose their software. Step 1, are you willing to program? If the answer is no, it's probably FlexLogger. FlexLogger would be a great choice for you. Doesn't require that programming skill and gives you all of the data you could ever want. If you are willing to program, it's worth asking, are you already very experienced in one of the languages NI supports, including C, C++, .NET, MATLAB, or Python? If the answer is yes, go ahead and use the NI DAQMX APIs with your language of choice. If the answer is no, and you're not familiar with any of those, then we definitely recommend using graphical programming with LabVIEW NXG. It'll give you a really great experience as you get started, give you those nice configuration-based windows to start interacting with your hardware before you get into the code, and even help you turn some of those configuration windows into code down the line. So this is a nice way for you to think about your next software investment. Another thing for you to consider is training. When it comes to that development time, a lot of that time is spent beating your head against the wall because you didn't necessarily take that week off in order to really dive into that technology. And I want to make it clear, NI has a lot of different training options available for data acquisition as well as for LabVIEW in order to learn what you need to learn to take a good measurement. There's free getting started content online. There are free on-demand training modules that are available for the first 30 days after you purchase and with a service contract. For the people who are willing to pay for an instructor-led classroom, you can go into a virtual-led instructor classroom with remote hardware, very useful in this current climate, as well as regional or on-site instructor-led classrooms, which will be a sit-down, live, in-person class. You'll have the hardware in front of you, and you'll work with an instructor to get to know it very well. And that's the end of software. We've covered the basics. We've covered beyond the basics. We've covered choosing your software. Let's put the pieces together. Starting with in-vehicle data logging. We talked a little bit about this at the very beginning of the session. We talked about how this is an application that we've worked on with real customers. But it's a complex task that has a lot of different I/O. So let's go through those same steps that we've just outlined in order to choose the right starting point for our data acquisition system. Step 1, we've seen this slide, we understand our channel counts. We know what signals we need to take. We know what sensors we need to measure from. We know what digital I/O we need. We know what specialty I/O we need. The fact that we have mixed measurements and some specialty I/O disqualifies DAC devices from our list. We are left with 2 DAC systems as our prime candidates for our data acquisition application. Step 2. Understand the DAC specifications. For each of those channels, I would go through and mark down the precision that I need, the amplitude of that signal, and the frequency of the signal that I'm trying to measure, which allows me to spec out the right resolution, range, and rate for each of the DAC cards that I need. In this case, as I'm continuing to decide between my platforms, both of these platforms have cards that meet my needs. So I'm still choosing between either PXI or CompactDAQ, no compelling reason to lock into one yet. Step three, questions and considerations. So I'm thinking back through some of the questions we asked and asking myself, what bus is right for my test? I need about 20 megabytes per second of data. Not a whole lot. Either bus could work for that. But I do need my bus to be portable. This is in-vehicle measurements. It would be hard to lug around a big PXI system. I'm going to be taking measurements in a vibration-heavy vehicle, so I need some amount of ruggedness as well so that my cards don't jostle themselves out of place by accidents. And my test needs are going to change relatively frequently. So it's a good thing that I have a modular system with me to make sure that I can tackle changing I/O. Which of course brings us to the likely candidate for this particular test, and that's CompactDAQ. CompactDAQ has the ruggedness that I need to handle vibration-heavy tests, the portability to be good in the car, and it meets all of my precision needs that I need for my data acquisition device. So this is likely my choice for my data acquisition system. Step 4, we select our software. I am a programmer. Let's say I'm a LabVIEW programmer. But I also want my team to be able to set up these tests and change these tests. In that case, I'm going to say that my team is not willing to program. And so FlexLogger suddenly becomes a very attractive choice that allows my team to also configure tests and data log without my being involved. So I come to my final solution, CompactDAQ and FlexLogger. There's a lot more work to be done. I still need to choose the right cards. I need to evaluate this against my budget. But this is the best way for you to narrow down your choices and find something that will work for your system long term. I promise you guys one last buying tip. So I want to recommend, as you're building out your next data acquisition systems, use the DAC system advisors. We have advisors for both CompactDAQ and PXI that allow you to choose the right chassis for your system, choose all the different modules that you might need, and then see the software and accessories that are relevant for the products that you've chosen. They really make it easy to configure your system and compare some of the different builds. So as you're speccing out one system, you might realize that you wanted an additional piece of I/O. That can be a great way for you to discover this. So definitely feel free to use the DAC system advisors as you build your next systems. But that brings us to the end of the slides. We've learned the basics of taking DAC measurements. We've learned the questions you should be asking yourself to help narrow down your selections. We've learned the software decision-making you should be making in order to find the right software for you. And hopefully, as you've been thinking through your own application, you have been narrowing down the options for your next test in your own head as well. So what comes next? Well, first we're going to do a live Q&A. I'm going to be hopping on my headset in just a little bit, and I'll be chatting with you guys live. Yep. And the next steps for you are to consult your resources. We'll have a checklist in there that will help you sort of answer some of these questions yourself. And we'll have resources out to other links like the advisors that I mentioned, as well as the Sensor Fundamentals webinar if you want to learn a little bit more about the hands-on nature of taking your measurements. So thank you so much for your attention. I'll join you in the live Q&A in just a moment. Thank you for being here.